Hello. Imagine that somebody gives us a linear differential equation with constant coefficients and expects us to provide a complete information, which means we want to know all the solutions. In other words, we want to know the general solution. If this equation happens to be homogeneous, then we know what to do, because previously we developed a fairly convenient procedure for solving such equations. What if this differential equation is not homogeneous? Then we are in trouble, because there is no general procedure for generating directly solutions of non-homogeneous equations. Fortunately, majority of the work can be actually shifted elsewhere, which is the main message of the structural theorem that we proved previously. Let's read the last paragraph. Let's read it from the end. We are interested in the general solution of the given equation, a non-homogeneous one. And the advice is, get a particular solution, just one solution of that equation somewhere. It doesn't matter how you get it. You borrow it, buy it, steal it, find it lying on the street, dig it out in your backyard, whatever. You just get one solution in some way, anyway. And once you have it, this YP, you then get a general solution of the associated homogeneous equation, which is easy, we know how to do it, and you put them together. So instead of finding all solutions of the given equation, you just need to find one of them, which is a big help. But still, that's a tall order. What can we do? How do we find that one solution? Well, now we'll look at one interesting approach. Let's have a look at an example. Y prime minus 2y is, actually, I don't care, some right-hand side. When we are given a differential equation, then the left-hand side defines an operator. And if this equation is linear and the coefficients are constant, then you have a nice linear operator. It takes a function, input y, differentiates, subtracts twice. And solving an equation is essentially a target practice. We are loading different y's into this shooting device called L, and you look where it goes, and you're trying to hit the target bx. So let's do some experimenting, okay? For instance, let's insert into this L, I don't know, logarithm. That's a nice function. What do we get on the output? Well, we have to differentiate and subtract double. So we look at it, and we don't see really anything because you don't know what you should be looking for. I didn't tell you yet. And I know what I'm looking for, but I don't see it there. So this is actually blind alley. This is a dead end. Okay, so let's try something else. How about if I load e to 5x? We all love exponentials, so let's try it. I differentiate, and the chain rule drops down to 5 exponentials, minus twice the exponential, and this is actually 3 into 5x. And now here I can see what I've been looking for, because the output is essentially the same as the input, the same type of behavior, the same type of a function, basic function, exponential, exponential. Is this just an accident? And the answer is no. If we ignore this business with a constant, and this is to be expected because y is multiplied by 2 in the equation, so yeah, there will be some constants appearing all the time, no problem there. If we ignore that, let's have a look at it. You have an exponential. You differentiate. What do you get? You get an exponential. You multiply exponentials by some constants, even if there are some other derivatives. Let's talk about general linear differential equations. You take exponential, you differentiate once, twice, 3 times, whatever. You still get the same exponential, perhaps with a constant dropping down, but we don't care about multiplicative constants now. You multiply them by constants. Well, we don't care. You sum them up, and you get your exponential back. This is a general rule. So, if we take some constant times an exponential with coefficient alpha, then on the output there will be perhaps a different constant, most likely, times the very same exponential. That's a very important observation. And now you can see what I've been looking for in this first experiment, and it didn't work out. I didn't get just logarithm on the output. So yeah, this isn't no good, but this one is good. Why is it good? Let's have a look at this. Somebody comes to you and says, I would like to solve differential equation. Y prime minus 2y is 6e to 5x. We are shooting, trying to hit 6e to 5x. Now we know that when we load exponentials into L, we get the same exponentials on the output. So I would say, okay, I tried e to 5x, and I see it didn't work out quite. I got the exponential right, but not the coefficient. But L is a linear operator. What does it mean? Well, if I take this 10 times, then the output will be also multiplied by 10, and so on. So why don't I take double here? If I multiply this twice, if I take this twice, then the output will be also taken twice, which is 6. I just figured out that this equation, this important equation, has solution yp, a particular solution, equal to 2e to 5x. Wonderful. And just out of curiosity, according to our theorem, we should now be solving also the homogeneous associated homogeneous equation, which is y prime minus 2y is equal to 0. We use the lambda approach, characteristic numbers. Lambda minus 2 is 0. Lambda is 2. So the general solution of this non-homogeneous equation will be yx is equal to, according to our theorem, particular solution, which is 2e to 5x. We were lucky to get it, but we are happy that's enough. And now we add general solution of the homogeneous equation. What is the general solution? We can get it from lambda. It's a e to 2x, and we are done. We just found a general solution of this differential equation. So there is something to it. It is useful, such an observation. Actually, in practice, when we do it, when we are solving equations like that, this type of approach is not the best one. Let me show you the best approach. I am trying to feed my left-hand side exponential e to 5x, and I expect that I will have to feed it several times, some multiple, because the chances that just an exponential gives me the output is very low. So what I'm going to do, I don't know what multiply I want to use, so I just used any multiple, a general one. And I simply ask, what is the output? Okay, I have to differentiate. 5 drops down, 5a e to 5x. I'm subtracting double of this, and I'm getting 3a e to 5x. Okay, so I loaded my left-hand side with this. The output is this, but I want this output to be this. I compare the output of my left-hand side work with the prescribed right-hand side of the equation. I compare them, I can see that actually 3a should be 6, so a should be 2. And I have my solution. I know that it's supposed to be 2 in front of the exponential. This is very nice because it's sort of like mechanical. It's an algorithm. You know that you should do this with a, and you solve it. This is like an algebra. You don't have to really think too much about it, like use your imagination too much, just a little bit here. So that's a very nice approach. It seems to work really well, but it's just for the exponentials. Can we use it with something else? How about, okay, let's try x squared. Powers, popular powers. Okay, if I put x squared into L, what is the output? I have to differentiate over here and subtract it twice. Can I put it together? Not really. Okay, so I'm mildly disappointed. It's a similar situation as this one because, okay, I have x squared on the output, but also I have x here. Actually, this is to be expected. If you take some power and put it into the left-hand side of a differential equation, then it gets differentiated, and you can expect some lower powers on the output. So what can I do? For instance, instead of looking at the powers, I can look at polynomials, because polynomials, there is the leading power and also all the lower powers. And when you put it through derivatives a polynomial, you differentiate, you get a polynomial again, and so on. Polynomials is a family that keeps shape under differentiation, addition, subtraction, multiplication by constant. So this is really another interesting family. We just have to sort of look at it from a slightly different point of view. When you put polynomial into L, on the output you get another polynomial. Very nice rule. Do we know something about this output polynomial? The answer is, well, you can never get higher powers. So the degree of the output, p tilde, is less than or equal degree of p. And typically it's actually equal. This will come handy. How can I tell? Well, if in the equation on the left you can see y, just y by itself, or multiply by some constant, but not differentiate it, then definitely your power will get preserved. And the degree of a polynomial also gets preserved. But it can never happen that the power goes up, of course, obviously. So that's another nice family, and as you can expect, here we have another example coming. Y prime minus 2y is 4x. Okay, how would we play it intuitively, like we tried it over here? Well, we would say, well, if I want to reach x, I should start it with x. But perhaps several x's. We always have to put a constant here. Even if there is no constant here or here, if it was just an exponential here, there is almost a zero chance that you feed your equation an exponential and you get an exponential out. There will always be some constant happening, almost always. So even if there is just exponential, you still want to put a e to 5x. You want to give this left-hand side some wiggle room, some possibility to adjust the output so that it fits. Okay? So I can see x here. I don't care that it's 4x. I just see x here, and I know that I will want to adjust. So ax, definitely on the input. Well, let's see. I differentiate. I subtract twice. And I can see that things do not really work all that well because, okay, I can fit the x's, but then there is this absolute term which is interfering. Not very good. So what I need to do is I need to give this L a chance to also adjust to the lower powers. So when I'm guessing a polynomial, I have to put all the lower powers as well. So this is a dead end, definitely not. What we want to use is ax plus b. A full polynomial, because those derivatives, they will sort of like send a also to lower powers, and we have to have a room to adjust, bottom line. So let's figure it out. I take derivative, I subtract twice the input, and now here we come to an interesting place. I want to take this output and compare it to the right-hand side of my equation, which is a polynomial. So I have to write this down as a polynomial so that I can see powers. Okay, what is the highest power here? X. How many times? Negative 2a. Negative 2ax. And that's it. Lower powers, which means absolute terms. Do I see absolute terms? Yes, I do. So I gather them all together into one nice expression, like that. So it's a linear polynomial, and I can see the absolute term and the coefficient in front of x. And if it was a high power, I would all of them separate like that, isolate. Okay, this is the output, and I'm comparing it with the right-hand side of my equation. Now, when you are comparing polynomials, you have to compare individual powers. Linear power here, absolute term, so there is no absolute term. You want 0 for it. This gives you equations for the coefficients of your output. Okay? Okay, let's have a look at them. It should be something small. I think I should fit it here. Okay. Negative 2a is 4, and a minus 2b should be 0. Okay, I can see right away that a should be negative 2, and when I put it into the second equation, I'm getting that b is negative 1. Okay? So, the particular solution, yp, x, should be, what is a? Here, negative 2, and here is my guess. That's important, that's the guess. Okay? Negative 2x minus 1. That should be the particle solution. Is it really? Well, we take this polynomial, negative 2x minus 1, put it here and see what happens. 4 plus 2, negative 2. Yeah, we get 4x on the output. Good. We've got ourselves a solution, and then we could continue like before, adding the homogeneous and so on. We don't have to worry about that now. We are now focusing on the particular solution. That's the important thing. We need to get it. So that's the approach. And it seems to be shaping really nicely. It does seem to work. We make a guess, which involves some coefficients which are yet unknown, and they give us a chance to fit our guess into the situation, to fine-tune it. The official name is called the undetermined coefficients method, which is long, and I will confirm it officially later. Unofficial name for me is the guessing method, because I'm guessing. But it's an educated guess, it's not a wild guess. It's a highly sophisticated guessing based on my knowledge of what's really happening, on my understanding of the situation. Okay, this was actually fairly successful. We now know how to solve two types of differential equations. Is there something more? Let's try how about what is missing? Exponentials, powers, trig functions. How about cosine for x? Well, I have to differentiate, which is negative sine, and 4 comes from the chain rule, so negative 4 sine for x minus 2 cosine for x. That's the output. Again, a mild disappointment. Okay, cosine survived, that's nice, but there is some extra guy. Well, again, I'm differentiating. It's a differential equation. When you differentiate, cosines become sines, and then cosines and sines and so on. More derivatives, perhaps. So, again, I have to look at it as a group thing. Here, I was talking about polynomials, but actually polynomials, that's a combination of powers. So I can see it like that. If a group of powers comes in, 1x, x squared, then on the output, again, I can see the same group combined together, 1x, x squared. And it goes the same with 1x, x squared, x cubed as a group and so on. So there are those groups that are entering, groups of powers entering and also leaving L. And here I have a group. The group consists of a sine and cosine with the same frequency. Because obviously, if on the input you have cosine for x, you can never get cosine 13x on the output. It will always be 4x. The frequency is preserved, but you have to take into account that sines, cosines, they change one into another using differentiation. So that's the natural group, a combination of cosine and sine with equal frequency. Here we go. A general observation. When you take a combination of cosine beta x and sine beta x, then in general, when you have linear differential equation with constant coefficients, many derivatives, then those derivatives will just change sines into cosines and so on. And then you put them together by addition and you group together cosines, group together sines, and what you get is just another combination of cosine beta x and sine beta x. So that's the third family that we know how to work with now. Okay, the inevitable example. Okay, y prime minus 2y is 10 times sine of 4x. Why not? Okay, we are experienced now. Let's use the undetermined coefficients, whatever method. Let's guess. Okay, what is the form or shape of the solution that I expect to see, to obtain? Well, to get any chance of obtaining sine, I want to see that on the input, but I don't know how many times. I need to adjust. So it's 8 times sine for x. But now when I run sine for x through my left-hand side, there is pretty much zero chance that I will get just sines on the output. I will also get some cosines. How do I make this appear, those cosines? Well, I have to also include them in the input. I have to give my left-hand side of the equation a chance to rearrange those things, to move sines into cosines, and perhaps cosines into sines in such a way that eventually the cosines will be gone. Okay? So sine, cosine with the same frequency, they always come in pairs, like that. You never see one without the other when you are solving. Okay, you can see it in the problem when it is given. But from now on, they will go together like brothers, okay, twins. Okay, what's the output? We differentiate. For A, cosine for x. So far, so good. Differentiate. Minus 4b sine for x. Okay, I'm subtracting it twice now. The input, a sine for x plus b cosine for x. Okay, that's the output. I will be comparing it to sine, so I want to see how many sines are there on the output. So again, I'm going to rearrange it. How many sines do I see? Well, I can see sine here, and also here. I factor out, and I get negative 2a. Let me start with a's over here, and minus 4b sine for x. How about cosines? Do I see cosines? Yes, here and here. So there will be 4a, and okay, I shouldn't forget, I'm subtracting twice. Cosine for x. Actually, if my blackboard was taller by about 15 centimeters or 6 inches, then I would put another line in there where I would multiply out this multiplication by 2. So that I don't have to keep it in my... One has to be careful. I will be talking about it later. Okay, not now. Here is the output. That's the output. I can see how many sines I have, but what I want, question mark, could this be made look like 10 sines of 4x? And also there are some cosines and I want them gone. So essentially I want to see 0 cosines. That's my aim. Okay? When I compare, again I'm getting equations. This coefficient is supposed to be 10 and this coefficient is supposed to be 0. Let's solve them. Okay, well, let's see. Minus 2a minus 4b should be 10, and 4a minus 2b should be 0. And you can notice I have two equations with two unknowns, perfect fit. This process that we are developing here, this procedure, always works like that if it's done properly, if the guessing is right. Okay, 2x2 system, you can solve it any way you feel like. Write down a matrix and use Gaussian elimination. If you enjoy determinants, Kramer rule is your baby. What else? You can try to guess the answer. Sometimes that works really well. Or you can just try to, go by the ear and, well, what can I do here? For instance, if I take the first equation, multiply it by 2, and add it to the second equation, then I should get something nice. Well, let's see. A disappears, and there will be negative 10 b's, and this should be 20. Am I right? I take it twice. Yeah, 20. So b is negative 2. Actually, I'm doing the Gaussian elimination. I'm just too lazy to write the matrix. Okay, if b is negative 2, then this is 4 plus 4, and a must be negative 1. And we are done. I know a, I know b, and where's my guess? What was I feeding my equation? This. This is my input into L. Now a is negative 1, b is negative 2. So the particle solution that we found is negative sine for x minus 2 cosines for x. And we can see that we were right. In order to get just 10 sine for x on the output, we do need some cosines in our solution so that things cancel each other out at the end. Okay? That's a very nice procedure. It seems to work, definitely. So let's try to extend it. Are there some more groups? And the answer is not really, because we don't have any more room here. But actually, yeah, that's true. There are no more groups. For instance, here, you may say, okay, wait a second, we gave up on it because the logarithm got preserved, but there was another guy. Why don't we, again, use this group approach? Why don't we say, okay, logarithm, and 1 over x is a nice group. Well, okay, so imagine that you take a combination of these two guys, you put it into your left-hand side, and there is derivative, and this derivative changes 1 over x into 1 over x squared, and if you want this group thing going, you have to include it, because it will be on the output. Okay, so we let 1 over x squared into the game, then it goes into the derivative, and on the output, we get 1 over x cubed. Up to a constant. It's the derivative of 1 over x squared is negative 2 over x cubed, but the constants, they can be pulled into a's and b's and so on. So the substance is the functions. You can imagine how this goes. Every time you allow in one of these powers, all the higher powers in the denominator also have to come. You get an infinite set, which is very inconvenient. You definitely do not want to play with infinite sets of functions. So, no, we were right. This is not a good idea. For the same reason, you cannot make good guessing for square root, because if you take square root into your game, you differentiate, you get 1 over square root of x. And you differentiate, and you get 1 over square root of x cubed, and to power 5, and so on, an infinite chain. So this is really the only elementary functions that have any chance of surviving when they pass through this L operator. The good news is that you can combine them. Let's have a look at it. What happens if you take a polynomial and multiply your exponential with it? Let's try it with our equation, okay? Because it's easy. This can be done also in general. So, derivative. I have to use the product rule. P prime x e to alpha x, and then I copy the first one and take derivative of the second one, and then I take twice the original function, and that's about it. So let's rearrange it. I'm going to pull out the exponential, and I get p prime x plus alpha px minus 2px, and that all multiplies the exponential. Now, what do I see over here? The answer is I see a polynomial, some p tilde x. It's a polynomial. I never integrate, just differentiate, so the power cannot go up. It can go only down, so the degree cannot go up. So this inequality is still preserved. Typically, the degree would be preserved as well, but sometimes it can drop, depends on the equation. So this type of expression, again, behaves in exactly the same way as we are used to here. We can also take exponential multiplied by sine, cosine combination, or these two guys, or all three together. If you get really bored, you can take polynomial times exponential times a combination of sines and cosines, put it into L, use the product rule for triple product, rearrange, and so on. You will see that the group survives. So this is the playground. This is the toys that we have at our disposal. We can solve differential equations in this way, perhaps. We will see soon. When on the right-hand side, we have some combination of these guys. So this looks very hopeful. We need to make some room now, and I will try to make this official. I will try to write down the general procedure for this guessing approach, and we will see. Okay, so here's the situation. We have a linear differential equation, constant coefficients. We look at the right-hand side, and we see a polynomial, some exponential, and cosine. Or perhaps we see the same group, but with sine. So a polynomial qx, exponential, and sine. Or perhaps both groups. And they should have the same frequency and the same alpha in the exponential. In fact, we always see both of them because they come in pairs. I talked about it. Sine and cosine, inseparable. So if we see just one, we just visualize that there's also the second guy actually present with 0 for q or 0 for p. We always see them as pairs. And when we see this on the right-hand side, then we do the following procedure in order to guess the shape, the right form of the solution. We just copy the exponential in our guess. It must be there so that it appears in the output. We also copy cosine and sine. And we have to make sure that they appear as a pair. Both groups must be there in our guess. And that's very important. And finally, we look at these polynomials. And instead of polynomials that we see, we write general ones. I use the word generalize. So that's those undetermined coefficients. And in this way, we generate our guess for the solution. And then we just substitute into the left-hand side, look at the output, compare it with the right-hand side. We get equations for these unknown coefficients, undetermined coefficients, and so on. The rest is sort of easy. Okay, so that's the main steps, how to generate the right form of the solution. And it works like a charm most of the time. Unfortunately, just most of the time. We have to add one more complication. Let me show you this complication. Here is an example. I'm trying to solve y prime minus 2y is equal to, let's say, 8 e to 2x. Why not? So I look at the right-hand side, and I just see the exponential. So that for me is the sign that I don't have to worry about sines and cosines. And I see 8, which is actually just the polynomial here, of degree 0. So what will be my guess? I think that my particular solution can be found. I'm not saying all solutions are like that. I'm just saying there is one particular solution, perhaps, that I can find in the form a e to 2x. Okay, what is capital A? Let's see. I take my guess for the solution, yp, put it into this left-hand side machine, and it does the following trick. It takes the derivative, and then it twice subtracts my input. And I hope that this will be equal to 8 e to 2x. Well, tough luck. This does not work. How come? It always worked in those previous examples. Suddenly, my guess totally disappeared. How is that possible? Well, what did really happen? We have shown that if I put my guess into the left-hand side of the equation, I get 0. Well, this actually means that this function is a solution to the homogeneous associated equation. And that's exactly it. Remember, last time we said, when we have a differential equation, we can pass to the associated homogeneous equation, and we actually need it. Here is the structural theorem. When we are trying to find all solutions, we should first look at the homogeneous system and find a general solution. How does it look like? Well, we pass to lambdas, we find the characteristic number, and then we form the general solution, which in this case will be the homogeneous solution of the homogeneous associated equation, which is some constant, let's say a, times exponential created out of 2, e to 2x. And yeah, that's it. That's exactly it. So it is obvious that if I feed e to 2x into my left-hand side, it must disappear because that's the homogeneous solution. So what do? I have here e to 2x on the output. Well, there is a trick, and the trick is like that. You have to take your guess, and if you find that it actually agrees with a homogeneous solution, that it disappears when you pass it through the left-hand side, then you have to protect it so that it does not disappear. And there is a cute protective trick. Instead of your original guess, you take it and you multiply it by x. And this will now survive the passage through L. And it's guaranteed that it will survive the passage through L. Really? Well, let's have a look at it. I write it as ax times e to 2x. Well. What is L? I have to take derivative. Product rule. A times e to 2x, that was the first part of the product rule, plus ax 2 times e to 2x. That was the second part of the product rule. Now I should subtract twice the input function, which is my guess, this guy, ax e to 2x. And now I look at it and I say, okay, wait a second. I can see 2ax e to 2x, 2ax e to 2x, that cancels. So that's the part which has disappeared due to this homogeneous thing interfering. And on the output, I just have a e to 2x. And I'm asking, is it possible to make this look like 8 e to 2x? Is that possible? And the answer is, of course it's possible. I just put 8 for a. And I got it. So it works. Okay. Notice that when we are passing this ax e to 2x, our guess, through L, then x actually disappeared in the process. And on the output, we have just the exponential without x. So that's the whole point of putting x here. It actually sacrifices its life to protect our guess, our original guess, the one that we would really love to have. Okay? That's the heart of the mechanism. Okay, let me finish this problem actually. What did we just do? I just found out that if I want a particular solution of my equation, I should use, where was my guess? Here. I should use 8x e to 2x. That's the particular solution. I also have the homogeneous solution over here. And therefore, when I put them together, according to the structural theorem, I get a general solution, not of the homogeneous equation that we have here. I get the general solution of this equation. And this general solution reads, according to the pattern, it's the particular solution, 8x e to 2x, plus the general homogeneous solution, a e to 2x. And of course, because I'm now writing down solutions, I should be careful adding the region of validity. And now we have the complete procedure. Finally, we have the blueprint for solving linear differential equations. First, we look at the homogeneous version, and we solve it completely. That was the previous lecture, using lambdas. Then, we look at our given equation, look at the right-hand side, and recognize that actually it's something that we know from the list. And therefore, we can make a guess. I would call it the baseline guess, natural guess. And then we have to start worrying. Is this guy actually a solution of our homogeneous version? And if it's not, I don't have to worry. I just use it, I pass it through L and get the coefficients and so on. And if it does solve the homogeneous equation, then I have to protect it. So I have to make a special correction. And then after I make the correction, I pass it through L, I find A, and so on. I get my particular solution. And then these two steps, the homogeneous step and the guessing stage, they get put together, and I have my general solution of the original problem. So that's the blueprint. Okay? That's how we will be doing it. Few remarks. First remark. Is there a nice way of recognizing that my guess actually agrees with some of the homogeneous solutions? And the answer is, well, you can look at the functions, or if you want, you can look at lambdas, because these functions in the homogeneous solution, they come from lambdas, from characteristic numbers of the homogeneous equation. So I have lambdas here, and there is a correspondence. 2 here, exponential here. Nice correspondence. I could actually do the same trick with my right-hand side. I can look at the right-hand side and ask, does it have a special type that could be described using lambda? And the answer is yes. This right-hand side has lambda equal to 2. Yes, because let's just mentally reverse the procedure. I'm solving a homogeneous equation, and if I see lambda equal to 2, I go to e to 2x. It's a two-sided correspondence. So I solve my homogeneous equation, and I see lambdas, and on lambdas, based on lambdas, I generate the general solution, the homogeneous version. And then I look at my given equation, I look at the right-hand side, and I do sort of like a reverse engineering. I ask, okay, what kind of lambda will generate this right-hand side? And the answer is lambda equal to 2. And then I just compare, are these lambdas equal? And if the answer is no, then I say, great, I don't have to do any corrections. My baseline guess will work. Wonderful. If those lambdas agree, then this tells me that I have an overlap in behavior. I should be careful. And therefore, I have to add corrective term. Let's move this line of thought a little bit farther. Now we know that essentially there are some lambdas that describe behavior. Lambdas describe the behavior of the homogeneous solution, and we can also use them to describe the behavior of the right-hand side. Now we know that these lambdas are not always just lambdas, but sometimes some of them are of higher multiplicity. There could be a lambda of multiplicity 2, 3, and so on. Does it have any influence? The answer is yes. Imagine that lambda has multiplicity 2. What does it mean? Well, if lambda has multiplicity 2, then we do not just see e to 2x in our solution. We actually see also something else. Remember the trick. So the homogeneous solution in that case would feature e to 2x or e to lambda x. Let me put lambda here now. And also b times, and here comes the trick, x times e to lambda x. Now, of course, this wouldn't happen here because this is just first order differential equation, but we are now talking in general. Okay, I have some linear differential equation, order 15, whatever, many lambdas, and one guy happens to be of multiplicity 2. Then the homogeneous solution features the exponential and also x times the exponential. So what happens if the same lambda appears on the right? Well, my guess will disappear when passing through L, so it doesn't help. But also, if I try to protect it, then it will also disappear when passing through L, because even the protected version becomes a part of the homogeneous solution. So what do I do next? I add extra protection. So then my particular guess would be a times x squared e to 2x. And you can imagine how it goes. If lambda is of multiplicity 3, then also the square root e to x appears in the homogeneous solution, and then I have to use x cubed to protect my guess. And again, when I then pass my guess through L, then this power disappears, even if it's a higher power. It sacrifices itself, and on the output there will be just the exponential, and I can compare and work it out. Okay? So we will see this in examples. It will start making sense. Finally, where does this idea come from? This idea for protecting using x. Let me give you a story. I talked about it earlier. When we have a linear differential equation, it has naturally some left-hand side, right-hand side. The left-hand side describes the behavior of a system by itself. If you do not mess with it, you just leave it alone, and it behaves in a certain way. And it prefers certain ways, which can be captured using lambdas. For instance, if you have a string, and you blink it, and it starts, oscillating, whatever, making a sound, then the frequency of the sound is determined by lambdas, because the movement of a string can be described by a differential equation. Things like people in physics, they know how to do that. We trust them. So this movement of the spring is decided by some lambdas, and you get frequencies for sine, cosine waves. That's what we will see on the spring if you use high-speed camera, things like that. So the homogeneous equation, that's the system by itself. And now, with the right-hand side, you reach into the system and you influence it in some way. And now, this lambda business, this correction business, actually has an interesting interpretation. The system by itself has some preferred ways of behaving. And if you reach into it with a different lambda, which is what we had in those previous examples, then you are essentially influencing the system in a different way, and so the system just incorporates it, which is this formula, yp plus yh. Yh is the behavior of the system, yp is your influence, or response to your influence, and they just get merged. Okay, and we can see from this pattern here that the response of the system is essentially of the same kind as was your influence. If your influence looks like this, also the guess for the solution looks like this. And we can see it over here. I have my influence, e to 2x, and I thought that the response of the system, the solution, should be also a e to 2x. It should be of the same kind. And generally, this is the case. But if your influence matches the preferred behavior of the system, then you are actually strengthening it. And the system reacts by being very happy and starting doing whatever it does with much more energy, with much more enthusiasm, and that's exactly this extra x. The natural behavior of the system, which is this, e2x, gets strengthened and gets larger and larger. So for instance, if you have a bridge, every mechanical construction, every system, when you put together something more complicated, has preferred modes of vibration, essentially. It has some vibrations that the system really likes, and you can recognize them by solving the left-hand side equation. You get those lambdas, and these are the frequencies that the system likes. So bridges, tall buildings, wings in an airplane, they have preferred modes of behavior, frequencies that they really like. And if you leave them alone, they will just, vibrate slightly like that. No problem there. Now, if you reach in with some influence which is different, then the system just takes it into account and, okay, business as usual. But if you reach in with a frequency which actually matches one of those preferred frequencies, then the system essentially takes the response, multiplies it by x, and you get this. And this is called resonance. And people who construct things, they have to be very careful about it. So for instance, when you are constructing a tall building, you have to take into account that it has some favorite frequencies. And now, could there be some outside influence with the same frequency? That's a good question. And where could such an influence come from? Well, imagine a town, a city, big city with high rises. And now when this there is a wind, let's say, going from the east, from the west, whatever. And as it passes between those high rises, it starts, moving left and right because, of course, it has to avoid those high rises. So the wind actually gets a certain frequency. It starts oscillating as well. And then it reaches your building, the one that you are just trying to set up. So when the wind reaches your building, it has some frequency already in it, determined by the shape of the city that it went through. And this frequency, if it matches the frequency of your house starting to react with enthusiasm, let's say. And this is not what you want. So what people do, what designers have to do, they have to check what kind of frequencies can come and fix the construction in such a way that the building or bridge, whatever, does not like it. Now, people became aware of this problem around, I think it was 1831 perhaps. In Britain, they had a nice bridge, suspended bridge, which was just standing there, minding its own business. And one day, a unit of soldiers was marching across the bridge. And by some lucky coincidence, or unlucky coincidence, the frequency of their marching matched the natural frequency of the bridge. And the bridge starting to react really happily. And of course, the construction of the bridge wasn't ready for that, and the bridge collapsed. Fortunately, casualties were light, no problem there. But the people started to worry. How is that possible that a bridge, which was strong and so on, fell down? So they started to investigate the situation, and they came up with this idea of resonance. And they started to worry about it. And this bridge happened 1831, perhaps. So we can read about it. But it's much more fun if you look at Tacoma Bridge from 1940. And this is actually something that you can find on the internet, because in 1940 people already had cameras. So you can actually view footage, actual footage of what happened to the Tacoma Bridge on one windy day. The Tacoma Bridge was spanning a canyon which was not going straight but twisting. And there was a wind passing through the canyon, and as it was twisting, it also gained a certain frequency. And the Tacoma Bridge started to feel frisky. And instead of just standing there, it started to undulate and oscillate like that. It was twisting, it was waving. Now we're asking what kind of waves? The answer is like 5-meter tall waves. There were cars standing on the bridge, and when you look it up on the internet, it's really cute. Well, in a bad way. The waves were so large that you actually couldn't see the cars when they were hiding behind them, when the wave came in front of them. These were really huge waves, and of course the bridge didn't last very long. Now, this is not exactly the case of resonance. For half a century, people thought that this was a case of resonance, and they were showing this as an example to students. Look, that's what happens if you ignore resonance. Later on, some engineers looked it up. They really investigated it thoroughly, and it seems that it wasn't exactly resonance, but rather a flatter, which is another phenomenon. A very unpleasant phenomenon for airplanes, by the way. They can take apart airplanes, the flatter resonance. So these are really serious concerns, but we don't have to worry, because our task is not to design bridges, things like that. Our task is to solve linear differential equations, so let's get back to them. This problem of resonance, which we can recognize by lambda, matching lambdas, can be solved by adding a protective factor, or 2, or 3, and so on, depending on the situation. And that's essentially it. There are no more traps. Now we can see the whole procedure. Let's formalize it, and then let's just work out some examples. Here we go. A big slide, probably the largest slide of this course. Okay, here we go. We have a linear differential equation with constant coefficients, the usual type. Now on the right we do not have 0, surprisingly enough, but some bx. Now we look at this bx, and we assume that it has the right form. Now, for, let's say, convenience, people tend to take these two terms and put them together by pulling out the common exponential. So that's just a reformulation, which is good for theory. From practical point of view, I actually sort of prefer to see them as two separate but close groups, okay? Related groups. Anyway, we look at this right-hand side, and we determine specific parameters that we need. We determine the constant in the exponential, this alpha. We look up this beta, and we look at the polynomials p and q, and we ask what is the degree there? What is the largest degree that we can see? And we call it d in this theorem. And then we form a guess. Let's have a look at it. How does the guess look like? We take the polynomials and we generalize them. So instead of p and q, there will be p with tilde, q with tilde. And the degree of these polynomials, of these two guys, should be at most d. So of course we put d to be on the safe side. Then we preserve cosines and sines and exponentials. We just copy them, which is exactly this stuff. So far, so good. And then there is an extra power of x. Where does it come from? The answer is that's the resonance. How do we recognize it? We go back into our data. After we determine alpha and beta, we create lambda out of them. Now notice that this lambda is created in exactly the reverse way to how we solve homogeneous equations. If your homogeneous equation has lambda, which is complex, then you use the real part to set up exponentials, and you use the imaginary part to set up sines and cosines in exactly this way. So when you are going backwards, from exponentials you create real part, from sines and cosines you create imaginary part. So that's exactly the formula there. Lambda is alpha plus or minus beta I. And you look it up in the list of characteristic numbers, and you ask whether there is an overlap. Do you see it there? Do you see it in this list? And if the answer is no, you set up m equal to 0. There will be no correction. If the answer is yes, you ask, how many times do I see it here? And that's the m, that's the multiplicity. Okay, so it corresponds to this picture. If lambda had multiplicity 2, we figured out that we would need x squared, exactly the same as multiplicity. Here, lambda had multiplicity 1, so just one correction was enough. It fits, multiplicity and correction, degree of correction. Okay. So that's essentially it. That's the theorem. And notice how the theorem is stated. It says, if you identify the important features of the right-hand side, then there must be a way of finding polynomials p and q that will create a solution of this form. It guarantees that if you guess it right, then you should be able to get some a, b, and c. Okay? There is some line down here. Let me have a look at it. And that should be it. So that's the mathematical point of view, and let's try it out. Okay, here we go. Let's see, what do we have here? A linear differential equation with constant coefficients. So far, so good. What are we supposed to do? Well, there are no initial conditions, so probably they expect us to find a general solution, so let's make them happy. We have a structural theorem, so we should first start with the homogeneous version. That's actually my favorite part. Okay. I pass to a characteristic equation. In other words, I pass to lambdas, informally speaking. Lambda is -2, which of course comes handy because it allows me to immediately write down the general solution of the homogeneous equation, which is what I call a homogeneous solution. YH is some constant times e to -2x. And let me add, just for the sake of completeness, the region of validity. I do not really need it there because this is not the outcome. This is just an auxiliary result. But let's be nice. After all, we should practice. We should get into the habit of always writing it. Okay, that's the homogeneous solution. And also we have this number -2 describing the behavior of the left-hand side. This will come handy later on. Okay, now according to the structural theorem, we need to get some particular solution somewhere. What about trying the guessing method? Why not? Okay, let's see. Right-hand side. That's the right-hand side B. I can see polynomial multiplying exponential multiplying sine of 2x. That's a good type of a term. Polynomial exponential cosine. Yeah, I like those terms. They fit into the category that we can handle. Do they belong together? Let's see. The same exponential, the same frequency, yes, they do belong together. Now, the theorem actually asks us to put them in one group. Why not? Okay, let's make the theorem happy. So I'm factoring out the exponential, and the right-hand side looks like this. Okay, let me also fit the order. Actually, mentally, for some reason, prefer starting with cosine. I don't know why. So it will also make me happy, okay? So it is 5x times cosine plus 9 times sine of 2x. Of course, it doesn't really make any difference. The order is arbitrary. So if you prefer starting with sine, go ahead. No problem. Okay, that's bx. Now we have to identify some constants. So of course we see alpha from here. Alpha is -1. We can see beta from here, which is 2, which is also from here. It must be a shared beta. And therefore, the overall lambda describing this behavior of the right-hand side, our influence, lambda will be alpha plus or minus beta I. So our influence is coded using lambda equal to -1 plus or minus 2i, which is different compared to the left-hand side behavior. So there will be no correction needed. This is wonderful. This means that m is 0, no correction. So this will make our life easier, definitely. Okay, then we have to determine d, which is the maximal degree of polynomial. Polynomial degree 0, polynomial of degree 1, so this is the winner, d is equal to 1. Let's form a guess. According to the theorem, our guess should have the following form. There should be the corrective term, but in our case m is 0, so it will disappear. And we really talked about it, there is no correction needed. But let's follow the theorem. Then there should be the exponential, I just copy it. And there should come some polynomial of degree 1. So instead of 5x, I'm writing general polynomial of degree 5, of degree 1, ax plus b. Okay, multiplying cosine to x. And then there is another general polynomial of the same degree. So instead of 9, I'm writing cx plus d, sine of 2x. Now, good question. Why do I write cx plus d if there is 9 in front of sine? Shouldn't I write just c? Let's go back to the general idea. I'm trying to find some expression that, if I feed it into the left-hand side, it will produce the right-hand side. Now, if I want x appearing in front of cosine, then it's natural to put it in front of cosine here on the input. But remember, the left-hand side is a differential equation, differential expression. So it features derivatives. And derivatives can change sines into cosines, and vice versa. So this x over here perhaps didn't come from cosine, but perhaps it came from sine. I don't know. And because I don't know, I have to allow this procedure the freedom to actually adjust to the situation. I have to make it possible for this left-hand side to create 5x out of here, or perhaps out of here, or perhaps from both. This can easily happen. So if I didn't put cx plus d here, I would seriously restrict the possibilities that the left-hand side has to do things for us. And perhaps then it would be impossible to find such a solution. Okay? That's why in the theorem it says that both p and q are polynomials of degree d, where d is the maximal one, not separate ones, not separate degrees, but they look at the maximal degree and they put it at both places. That's important. Okay, that's our guess. Actually, from practical point of view, it's better to multiply out, definitely. So let me make another row over here, or another line. Okay, x is gone, so it will be just ax plus b times the exponential times cosine plus cx plus d times the exponential times sine. And this brings me back to how we started this lecture. Intuitive way of doing this. I see a group, and I say, okay, how do I handle it? I copy sine, I copy the exponential, and I just generalize the polynomial, which I did. Now, the tricky part is that I have to generalize it to a higher degree, but that's because I see it as a group, and I see that the highest degree is 1, so okay, I'm generalizing to degree 1. And then I did the same for this group. I copied cosine, I copied exponential, I generalized polynomial. Okay, so it's natural to see it like that. Now, what do we do with this yp? We have to put it into the left-hand side, look at the output, and compare it with the target. And this will be long. Okay, so what is L? L takes derivative of the input. What is the derivative of the input? Okay, addition, good. We differentiate each part separately. Multiplication, not so good, because there's 2 of them. So we have to use the special version of the product rule. We differentiate the first guy and copy everything else. Then we copy the first guy, differentiate the second guy, and copy the third guy. Then we copy the first guy, copy the second guy, and differentiate the third guy. I have to use the chain rule, of course. Okay, I hope I have enough chalk, because this will be interesting. Now I have to do the same trick, the derivative, with the second term. So, okay, I got practice already, so this should be easy. Differentiate the first, differentiate the second, and differentiate the third. So far, so good. That was the derivative. Now I should add double of y. Okay, so let me mark it like that. That was the derivative. And now I have to add twice my guess. Well, let's see. ax plus b e to negative x cosine to x plus cx plus d e to negative x sine to x. My hand is starting to hurt. Okay. Let's see. Now we have to take this output and rearrange it into the proper form, which is polynomial exponential sine, polynomial exponential cosine, or the other order, whichever way you feel. Okay, let me start hunting for cosines. Okay, so the first group will be the exponential and cosine. Where do I see it? I see it over here, and there is a in front of it. Okay. I can see cosine over here with exponential, and there is minus, and this polynomial in front of it. So when I factor exponential, I factor cosine, there will be minus ax and minus b. So far, so good. Okay, where else do I see cosine? I can see cosine over here. And I have to be careful. After I factor out the cosine and the exponential, there will be 2, there will be this polynomial, and there will be another one from here. Okay, I can live with that. So there will be 2cx, and I'm running out of room. This is unpleasant. And there will be plus 2d. Okay. Do I like it? Moderately so. And finally, I can see cosine over here. How many times is it there? It's there 2ax times. So I factor out 2ax, move it here, and it cancels with minus ax, and it will be there just plus once. So far, so good. And then there will be plus 2b. Plus 2b comes here, and it becomes plus b. I sincerely hope that I got it correctly. I don't really have enough room. If I am doing this on paper, I definitely do first multiply out the brackets. All the parentheses here, I would multiply it out. I would definitely distribute 2 at all places so that I don't forget. And only then I would start collecting the terms. This is much safer. This is the perfect opportunity to make a numerical mistake or oversight mistake. And it's deadly. Okay, I don't have room, so I have to be, this is a challenge. I'm just now doing something which is much more interesting than some adrenaline sports. This is real adrenaline, okay? Bungee jumping. It's easy compared to this. Okay. Here we go. I'm hunting for signs. Okay. Let me start here at the end. I can see sine here, and it's twice cx plus d. So it's plus 2cx, I suspect. There will be something with a's also, and plus 2d at the end. Okay, so far so good. Do I see another sign? I see a sign over here. And it is here negative 2 times. So negative 2ax, and minus 2b. Okay. And then I can see sign over here. And this sign is taken minus time and this. So I'm subtracting cx, and therefore it's here only once. And I'm subtracting d, and therefore it's here only once. Okay. And finally, I can spy sign over here, which is c times. So there should be plus c without x. And no constant. Okay. I sincerely hope that I didn't make a mistake, otherwise I'm in big trouble. Okay. Now, can I afford another line? The answer is no, but I have to. Okay. Or perhaps let me cheat it. This is a polynomial where x is taken a plus 2c times, and then there is the absolute term, which is a plus b plus 2d. This is a polynomial which has x part, namely minus 2a plus c times x, and then it has an absolute term, plus. And let me start with minus 2b plus c plus d. So I have a polynomial, exponential cosine, polynomial, exponential sine, and I want this to be the given right-hand side, for which I don't have room. Okay. What does it mean? Well, let's compare. How about cosine? E to negative x cosine. How many times it is there? 5x times. 5x, which means this has to be 5, and this has to be 0. Okay. The sine part. Exponential sine is there 9 times. Exponential sine is there 9 times. And x does not appear at all. This should be 0. How many unknowns? Undetermined coefficients. The answer is 4 of them, a, b, c, d. How many equations? 1, 2, 3, 4. It fits. If it happens that this does not fit when you are solving a problem, then in 90% of cases you made an error when setting up the estimate for your, or guess for your solution. So at this stage, if I make a mistake, I will recognize it over here. There is another possibility that the number of unknowns and number of equations do not fit, and this happens when you forget the correction. Typically, then, some of the terms disappear, and suddenly you do not really have a chance to obtain a match. So disappearance of a term means you overlooked a correction, and this balance between number of unknowns and equations typically means that the guess wasn't right structurally, that there are some terms missing or perhaps some extra terms. This can also happen. Okay, let's see. I have 1, 2, 3, 4 equations with 4 unknowns. Do I feel like solving a 4x4 system? Not really, because it's huge. Gaussian elimination is not too bad. I don't have room for it. So I look at it and I say, wait a second. This equation has just 2 variables. This equation, the same 2 variables. It's a 2x2 subsystem. Let's have a look at it. Where will I have a look at it? Here. I'm really getting short of room. So over here, a plus 2c should be 5, and negative 2a plus c should be 0. What happens if I take the first equation, multiply it by 2, and add it to the second equation? 2 number 1s plus number 2. Well, if I do that, then a's cancel, and there will be 4 plus 1 is 5 c's, is equal to, I double it, is 10, c is 2. If c is 2, then from the second equation, c is 2, a is 1. Great. Let's have a look at the remaining equations now. This equation over here reads a plus b plus 2d is 0, but we know that a is 1. So I can put 1 here, move it to the other side. b plus d, 2d, b plus 2d is negative 1. By the way, I got integers for the answer. Because this is a school problem, I expect integer answers, and I got them, so this makes me optimistic that I didn't screw up. Wonderful. So far. b plus 2d should be negative 1, because there will be still more opportunities to screw up. So yeah, let's not start celebrating prematurely. This I handled, this I just wrote down, this I handled, this one. Okay, how much is b? I don't know. I know c. C is 2. And on the right-hand side, there's 9. So I take this 2, I subtract, and it will become 7. And again, if I were solving it, especially on an exam, I would do all the calculations on paper, carefully. I wouldn't do them in my head because this is dangerous, especially in a high-stress environment, which the exam is. Okay, minus 2b plus d. Okay, I will try the same trick. It worked before, it will work now. Double the first equation, add it with the second equation. 2b minus 2b gone. 4d plus d is 5d, is 5. d is 1. Let's see where they put it. Over here, d is 1, b is negative 3. So, finally, I identified coefficients a, b, c, and d that form my particular solution. Now, quite frankly, on a test, I would probably not write the particular solution, and you will see why. But let's roll with it. An important thing, I have to look at my general form, and it's a good idea to somehow emphasize it, so that when I'm looking for it, I find it. That was my guess. This is how I guessed that the solution should look like, and now I determined a, b, c, and d, so here is where I put them. A is equal to 1, b is equal to negative 3. X minus 3 times e to negative x times cosine 2x. Okay. C is 2, d is 1, 2x plus 1. E to negative x sine 2x. So that's the particular solution. I'm not writing region of validity because immediately I'm going to pass to a general solution of my equation, of the given equation, not the homogeneous one. That was easy. This equation has the following general solution. And here it comes. Yx is equal to, and now I have to copy yp. According to the formula that, okay, let me go back. The structural theorem says yp plus yh. I see there. So yp, I just wrote it. I have to copy it. Okay. X minus 3 e to negative x cosine 2x plus 2x plus 1 e to negative x sine 2x. So I copied it, and now plus yh plus a e to negative 2x, x belonging to real numbers. Hooray, we are there. Let me just check that I got the constants right. 1 and 2, 1 and 2, 1 and negative 3. Okay, I got integers, which is hopeful, so I think this is correct. Just, you know, let me just, okay. Okay, yeah, it's correct. So that's the right solution. And I'm really glad that I got it, because there are so many opportunities to make a tiny mistake that totally throws it off. So I'm actually nice. On a test, if you end up with 17 over 25 for your A, check your calculations again, please. Okay? What did we just learn? Well, first of all, I think that we learned that I'm not going to ask a problem like that on a test. Definitely not. I mean, that was beastly. Especially, imagine that this differential equation is of order 2, which on the test it will be of order 2 or even 3. So imagine we took one derivative of this triple product and it grew like that. Now imagine taking second derivative. That would be beastly, and my conscience doesn't allow me to ask you a question like that. So I will ask a question where this calculation will be slightly more friendly. The trick is, I want to see how you understand the procedures, and I can figure it out from a much nicer problem. So don't worry, on a test, the right-hand side will be, let's say, more friendly. But other than that, this is actually a fairly good problem. On a test, you will have to do the homogeneous part, make the right guess, determine A, B, and C, write down the general solution. That would be stage 1. And then you will also get initial conditions. So you take this general solution, you substitute initial time, and so on, figure out the constant here. Okay, so that's essentially the whole thing. Notice that I'm being nice on myself. When I'm doing the general solution for the homogeneous version, I'm using lowercase a, and here I'm using uppercase A, B, and C, and so on. Why? Because I like myself. If you start using the same A, you will most likely mess it up. At least that's my experience, okay? I'm not going to take it as a mistake if you use lowercase a here, and B, and C, and D. And if you work it out correctly, I'm just going to raise my eyebrow a little bit, but okay. But there is a high probability that you mess up. So it's my advice to definitely sort of separate this mentally by using lowercase and uppercase. Some students do it the other way around. Do I care? No. The important thing is you have to be organized. That's very important. If you have a procedure which is that long with many steps, organization is very important, okay? So try to keep the whole structure in your mind and see how you go through those individual stages. What is the aim of each stage? Where should it lead you? How should you stop each stage? Where should you stop it? Here, at this, I have a particular solution. Happy. I go to the next stage, and so on. So this is important to keep this in mind, the general flow of information of the work. Other than that, that's essentially it. Let's talk about the simpler forms, because as I said, it doesn't really happen all that often that you can see all three parts in your right-hand side. So that's one thing that I would like to talk about. What happens if there is something easier? And the answer is you just ignore it. So here is a helpful slide. If on the right-hand side you just see a polynomial, then you guess a polynomial. Why not? Perhaps there will be a correcting term. And the same with exponential, the same with cosine and sine. If you just see cosine sines with polynomials, you ignore the exponential if it's not there. The tricky part is when you are deciding on corrections, when you are comparing right-hand side, left-hand side behavior. How do you get lambda if there are some parts missing? Well, if there is a part missing, you just put 0 for that corresponding part of lambda, real or imaginary. So let's start from the bottom. If your right-hand side features cosine, sines, polynomials, but no exponential, then there is a 0 for the real part, and your lambda is just a purely imaginary number, which is exactly what you see at the end of the last line. Okay? By the way, notice that the polynomials are not reflected in lambda. That's interesting. That's because the polynomials do not really substantially influence the behavior from the, let's say, real, from nature point of view. Okay? The polynomials, they are just modifying existing behavior. So we don't care about polynomials in this lambda. Let's move to the middle part. If your right-hand side is a polynomial times exponential, then you put the exponential here for the real part, and for imaginary part you put nothing because there is no sine, no cosine, so why would you put anything there? And you get real lambda, lambda equal to alpha. So it makes sense. Let's go on the top. If you have just a polynomial on the right, then there is no exponential, no cosine, so you put 0 here, and you get lambda equal to 0. Because there is nothing substantial on the right. Yeah, that's it. Lambda is equal to 0. So that's how we handle those simple cases. Another good question which is floating around here, and perhaps you do not see this question, but when you start wondering, okay, I said, okay, the same frequency, the same exponential, these two guys belong together. Nice. What if there was frequency 2, there was frequency 3? Or what if there were different exponentials? Then I would have to treat it as two different cases. One case would be with exponential sign, and I would imagine that there is also a virtual pair with the same exponential and cosine with the same frequency. And I would handle it in exactly the same way that I did over here. And then there would be another group with perhaps different exponential or different frequency. And again, I would see it as a representative of a pair with cosine sine, and I would handle it in this way. And what would happen next? So we need a theorem, one more and the last one for this part. So here it comes. This is called the superposition principle. And let's read it from the end. Okay? We have a differential equation, linear, and we just look at the left-hand side, and the left-hand side determines a certain operator or mapping, Ly. Or you can see Ly just as a symbolic notation for the left-hand side of the differential equation. Now let's have a look down here. We are trying to solve equation which has the form the left-hand side is equal to b1 plus b2. And that's exactly it. What do you do when the right-hand side actually consists of several components, of several parts, of different nature, so that you cannot connect them? Okay? It could be, for instance, that on the right you have e to x plus 5x. These are totally different animals, and you can recognize it by lambdas. This guy has lambda equal to 1, because it's 1 times x. This guy has no exponential, no cosine, no sine. This guy has lambda equal to 0. Different lambdas means these are different guys. So that's exactly what we see here on the right at the end. Our equation has two different guys on the right. How do you react? And now let's read it from the top. You take your equation, and you solve it with just one term on the right, with just b1. And you get some solution. Then you solve it with the second part of the right-hand side, with the second term in the right-hand side. And you get solution y2. And then you add these solutions, and it will solve the equation. So it looks like the addition is passing from the right-hand side to solutions, essentially. Okay? This is called the superposition principle. Here it is formulated for 2 terms, but it's the same thing with 3 terms, 4 terms, 5. So when you look at the right-hand side, and you see that it has several terms in it, which are of different nature, then you simply solve the equation for each of them, you get your particular solutions, and you sum them up. Very simple. And some people do it, even some students do it, when they come to my exam, and I give them a problem where there are different terms, which is actually always. Then they solve each differential equation separately, and they put the answers together. It works. I prefer a slightly different way. I know that I will be adding those solutions at the end. So what I do, I actually add them already at the guessing stage. And that's what I recommend, but as I said, not everybody follows it. Some people prefer the other way. I don't have any problem with it. Let me show an example, and that's actually the last example of today's lecture. It will be substantial, and it will be really close to an exam example. So it will be a good example. Okay, Here's our last example. Let's find the general solution. Here we go, 2 stages. In the first stage, I guess I can call it A or something if you want to be organized, I'm going to solve the homogeneous version. So I will look at it, and I actually don't need to copy it. I just look at it and pass to characteristic equation. But okay, since this is a lecture, let me do it properly. So that's how the homogeneous version looks like. And now I pass to lambdas. So as I said, you can do it easily just from the given equation. I find the roots, let's say by factoring, my favorite way. This is a school problem, so I'm highly optimistic. Lambdas here, definitely. To get 1 at the end, this is the only source of nice numbers. And I need to get minus here, so minus minus. Does it work? Well, of course it does. This is actually lambda minus 1 squared is equal to 0. That's the famous identity. I could have thought of it right away, pass from here to here, because that's a popular case. Appears very often at school. Okay, we have lambda, our characteristic number equal to 1, but with multiplicity 2. That's important. That will definitely be important. Now, let's recall the special trick for lambda of higher multiplicity. First of all, from lambda equal to 1, we generate the exponential, in this case e to 1 times x, which is e to x, but that's not enough for the fundamental system. Fundamental system needs to have 2 terms, because we have, well, multiplicity 2 and equation of order 2. And here's the trick, x times e to x, how to find the second vector. Now, we should not mix it up with the correction that we just discovered today. This is a totally different trick, serving a totally different purpose, just by coincidence, interesting coincidence. It is actually done in the same way. I multiply by x, but it's a different animal. Now I will take this fundamental system and create a linear combination, and in this way I generate the general solution, YH. And okay, just to feel better, I will also attach region of validity. There is no restriction anywhere, x belonging to real numbers. So far, so good. So that's my favorite part. Let's pass to the next stage. We need to figure out the non-homogeneous version to find some particular solution. How do we do it? Well, we look at the right-hand side. How does it look like? I can see a bunch of terms which are added. It's a linear combination of different terms. Now, can I simplify it by putting some of them together? What is the nature of these terms? Well, they seem to be different, like e to x, and I don't see e to x anywhere else. So e to x is just a, individual guy sitting here, not talking to the other guys. Everybody here is an individual. Okay, so I've got 1, 2, 3, 4 terms, actually. Sometimes it's easy to overlook, but let's say 13 could be added with x squared into 1 term, because it would be a polynomial. So that's how I think. If you are not sure, you look at lambdas, which is something that we will need anyway. So let's do our guessing. First, I'm going to do an unofficial guess. So I'm not going to call it YP, definitely not, which will be the basic stage. So let's see. I see e to x, and I think it's an independent term. So how do I guess for e to x? Well, we know that we should copy the exponentials, definitely. And then we should copy sines and cosines, which I just did. That was easy. And then we should take the polynomial, which is in front of it, and generalize it. Now, one would think there is no polynomial, but there is. There is 1 times hidden. This is something that one has to be careful about. So when I generalize, I should put a. Now, you should see that there should be some a, even without knowing this generalization trick. Do you remember at the very start, when we were trying to put exponentials into left-hand side and shooting for the right-hand side? Remember how sometimes the constant didn't just fit? So we had to put a constant here so that we can reach the target. That's exactly it. I have to give my procedure a chance to adjust the input. I adjust it by taking it twice, 15 times, half times, I don't know, but I have to give the procedure a chance. Okay? So definitely, whenever you're writing a guess, there must be at least 1 unknown, at least 1 undetermined coefficient. If it's not there, you're making a structural mistake, and it will be bad at the end, unless you are really lucky. If this a happens to be 1, then, and you forget, you will not discover your error, but it will be there. Okay. What is the lambda for this? Lambda for this term is 1, because there is no cosine or sine, so no complex part, and from the exponential I get 1. Let's compare it. Does it match lambda from the homogeneous stage? And the answer is yes. And it just not just matches, but it actually matches it twice. So there's a match. The intensity of the overlap is large, multiplicity is 2. We have to make a correction. And the correction means that I have to take this term and multiply it by x squared. Because if I don't multiply it, it will be just one of the guys in the homogeneous solution, and it will disappear after I pass it through the left-hand side. Yeah, we talked about it. If I put just x, again, it will be here in the homogeneous solution, it will disappear. I have to put x squared. And now I'm already building my particular solution, including the correction. Let's move on. Okay, the second term, 27e to negative 2x. That's a lot of exponentials. Probably there is a reason for that. How do I guess? I copy the exponential, and I take the polynomial in front of it and change it into a general polynomial, which in this case would be b. And this is a good opportunity to warn, because when people get used to a specific way of creating general guesses, they sort of tend to think ax plus b, ax squared plus bx plus c, a, so on. So what happens if I put a here out of habit? I'm in big trouble, because then this a would actually have to serve two masters. It would have to serve two purposes. And one single variable cannot serve two purposes at the same time. That would be impossible. So most likely, at the end, I would end up with two different values for a, which is a big trouble, of course. So I have to be careful. I have to use different unknowns here. Okay. What is lambda here? Lambda is negative 2. Let's compare it. Do I see negative 2 over here in the list of lambdas for the homogeneous equation? No, I don't. No match. No correction. So I just take this guess and copy it. Wow, that was easy. Okay, it's a different lambda, so it's a different term. Cannot put them together. That's confirmation that I was right. These guys are different. Okay, this one was done. 13. What is 13? That's just a polynomial. So I'm copying all the exponentials. I just did. I'm copying all the sines and cosines. I just did. And I take the polynomial and I generalize it. Here we go. Lambda. No exponential. And no sine cosine. 0. It's 0. Again, no correction. So this guess gets just copied into my YP. It's shaping up nicely. The last term, some number times sine. How do I generalize? I keep exponentials, which means I keep nothing. I keep sine, I generalize the polynomial. And then I have to make sure that I get the whole group, sine and cosine, as a pair in my guess, always, always. So, I could start with sine or with cosine, it doesn't make really any difference. And just to conform to the theorem that we had, I will start with cosine. So I copy cosine because it is virtually here, they always come in pairs. So I take this virtual cosine, copy it, and put constant in front of it because that's the highest power of polynomial. And it has to be called differently, a, b, c, d. And then I do the same trick with sine. I copy it. I copy the exponential, which is non-existing, and from 25 I will generalize to e. And that's it. And as I said, if you want, you can do it in the opposite order, and it will also work. No problem there. Sometimes I also switch it, because it doesn't really make any difference. But I actually, for some reason, prefer this. I don't know why. Anyway, here we go. How about the corrections? Do I need to apply a correction? Lambda is, okay, no real part because there is no exponential, only imaginary part, 2i. Do I see it on my list? No. No match, no correction. So also this one gets inherited by my guess. So what I just did, looking at lambdas, they're all distinct, so really these guys are separate. I formed the basic version of the guess when I was just changing the shapes, And then for them, I also looked up corrections, and I applied the corrections, which was necessary in one case, and this is my official guess. That's what I will work with. And that's the important line, I'm emphasizing it. Perhaps I can even make some, okay, little house here. I want this to be prominent. I want this to stand out. Okay. What next? I have my guess, and I should substitute it into the left-hand side. So if I had a lot of room here, I would first find the derivative. Then I would find a second derivative, and then I would substitute them. And I actually recommend that you do it that way, because it's safer. I don't have much room, so I will try again this adrenaline way. I will try to do it slightly differently. So, what is expected of me? I should take the second derivative, and I'm not quite ready for that. Then I should subtract twice the first derivative, and I'm not ready for that either. And then I should add y, and that's something that I can do, because y is sitting here, looking at me nicely. I just make one little change. I will switch the order here. I will write it as ax squared e to x, because I will take derivatives later on, and I can treat it as a polynomial times exponential. It's more convenient. Okay, b e to negative 2x plus c plus d cosine 2x, I think. Yeah. E sine 2x. Okay. Now, what happens now is essentially routine. It's a manual work, lumberjack work. We just beat it with an x, and at the end you get it. The real mental work is over here, on the level of creating the right guess. And if you create the right guess, the rest should be more or less a formality, unless you overlook something small, which happens. So, this is the critical stage. And if you are, let's say, uneasy about some aspects of it, or if you are not quite sure what you are doing, I prepared a practice video, a bonus video, where you can practice this guessing stage. And I'm also trying to clarify some, let's say, sticky points, some aspects that beginners sometimes find difficult. So if you want, check out this practice video. Strongly recommend it. Anyway, I'm confident that I did it right. So I'm confident that I will well, I'm not confident. I'm hoping that I will do this right. Okay, what am I supposed to do here? I'm supposed to find a derivative and put it here into this group. So let's differentiate. Product rule. I differentiate the first part to ax, copy the second, plus copy the first one, and differentiate the second. That was easy. I differentiate here, minus 2b e to negative 2x. I differentiate c, and it's gone. Poor guy. Okay, that's life. I differentiate cosine 2x times d, the chain rule. So 2 comes out, and from the derivative also minus comes out. So minus 2d sine 2x. And finally, I differentiate the chain rule. 2 comes out, plus 2e cosine 2x. And I just made it. Good. So that's my first derivative, which I put over here. And here I need second derivative. Okay, how optimistic am I? This optimistic? We will see. Okay, I differentiate. Product rule. I differentiate here. 2a e to x times, I differentiate here, plus actually, plus 2ax e to x, plus product rule. I differentiate the first guy, 2ax, copy the second, plus copy the first, differentiate the second. So far so good. Derivative here, negative 2 drops down, creates plus 4, b e to negative 2x. Differentiate, this becomes cosine, 2 comes out, negative 4d's cosine 2x. Differentiate here, it becomes minus sine, so minus. 2 comes out, creates 4e sine 2x. Yeah, I made it. Running out of chalk, it seems. Okay, this is intensive. I hope this is correct. And now, the next stage should be that I multiply out all the brackets that I can see in this expression. Why? Because it's smart. It's safe, okay? But I don't have the room. So I'm going to do something which I definitely do not recommend you that you do. Or rather, I recommend that you do not do what I just do, okay? So I will try to hunt now without multiplying out the bracket, especially this -2 is dangerous. If I overlook this -2 at some stage, I'm in big trouble. So, okay, let's see. Let's hunt for things. I have to take this output. That's the output of the left-hand side, and I want to compare it with the right-hand side. In order to do that, I have to identify the groups. Let's start with e to x. Do I see e to x? And the answer is yes, and I can see it with x squared, with x, without. Let's put some order into it. How about x squared e to x? Do I see it somewhere, anywhere? The answer is, well, yes. I can see it here. And I can also see it here and here. How many times do I see it? Well, every time there is a, so I keep it as a group. How many times do I see this group? Once, another once, it's twice, and then it's subtracted twice, so it's gone. So x squared e to x disappears, which is expected, because I didn't put it there so that it appears on the output. I put it there so that it protects my guy. And it did. It just died in the attempt, but it succeeded, hopefully, in protecting e to x. Okay, x e to x. Do I see it somewhere? Okay, I see it here, and I see it here, and I see it here. How many times? 2 plus 2 is 4 times. -4 times, it's gone. So this all fits. It works exactly the way I wanted it to be. X e to x disappeared as well. Is there e to x left? The answer is yes. Over here, this little guy. So 2a e to x. Okay. And that's it for the first group. And now I can compare, actually. I can start comparing. Well, let's see. How about the second group, e to -2x? Do I see it somewhere here? And the answer is, well, for instance, I could see it over here. I can see it over here, and I can see it over here. And again, there is b always with this exponential, so I treat it as a unit and I ask, how many times do I see it? Let's not forget multiplication. -2 times -2, I can see it 4 times, 5 times, 9 times. 9b e to -2x. Just out of curiosity, does it look good? 9b should be 27, b is equal to 3. That looks good. That looks hopeful. Okay, let's move on. The next term I want to compare is this constant. Do I see a constant here? The answer is, oh yes, I can see c here. And it's gone from the other derivatives. So that will be very nice, very easy. Okay, the next guy, cosine. Do I see cosine? Because it's virtually here, and I put it in the first place, so let's put it in the first place. I see cosine with d, and I can see cosine with e. So let's make some resemblance of order in it. Okay, let's say that I collect the d guys first. So there is d once, and d -4 times, which is -3d. So far, so good. And then there is this 2e, but let's not forget, multiply by -2, -4e. You really shouldn't do that, okay? This is really risky. Okay, let's hunt for signs. I can see signs here, and here, and here. And again, they come in 2 different flavors, with d's, with e's. Let's go by alphabet. How about the d guys? -2 times -2 is 4d. How about e's? 1 here and -4 here, it's -3e's times sine of 2x. So I think this could be okay, hopefully. And this is the output. It has the right form because the terms in the output are of the same shape, of the same form as the terms of my right-hand side. So I can compare term by term. I look at the first term here. I look at the first term here, and I can see that this constant should be 1. Then I compare the second term. 27 27. Let's compare the third term. 13, 13. Cosines. How many cosines do I see here? That's the virtual group. This should be 0. But I can see some sines. How many of them? Negative 25 sines. Again, that's a lot of sines. There is probably a good reason for that. Okay, by the way, before we move on, notice that, let's say, this group, e to negative 2x, in all this work, never interfered with the other guys. Because e to negative 2x, when you differentiate, add it, whatever, can never become e to x or cosine or a number. It's simply playing its own game. So when you look at it like that, you can actually see that we are doing in parallel 4 calculations. We are working with the exponential e to x, with some multiple by x, corrective term. Here we are working with e to negative 2x. Here we are working with a constant. Here we are working with sines and cosines. These are 4 parallel processes. And that's exactly why some people feel that perhaps if I'm doing 4 parallel processes, I can do them separately. So I could just take the guess, b e to negative 2x, work out the derivatives, which perhaps is much easier, and work out the coefficient b. And 1/4 is done. Then I do the same for C, then I do the same for this group, for this group. So some people prefer to split it into 4 separate calculations, determine the particular solutions, and then put them together at the end. So this is really a viable way. For me, I sort of prefer this way, although it's a little bit tricky at this stage, but it saves some room. I saved a few lines of calculations, actually. 2, actually. Well, okay. I have my equations. Undetermined coefficients, and I know the outcomes. So let's have a look at it. A should be 1/2. Now, this is a bit unexpected, especially on a test, and I will get mightily suspicious, but actually 1/2 is not bad, and I figured that perhaps we can see some example with a fraction. Yeah, why not? I mean, real life is not nice always. You don't always get integers. So this is just a reminder that things can get tricky when you are doing it in applications. Okay, 9b should be 27, b is 3. Now, this is more like the exam problem. That's what I expect at the exams. C is 13. That's a nice number. Wow, this gets tricky a little bit. So perhaps let's make a little corner here. Push corner. Minus 3d minus 4e should be 0. And 4d minus 3e should be minus 25. Okay, how do I solve it? Can I guess the answer? Probably I don't see any opening for guessing, so I will have to do some work. That's life, sometimes you have to work. What happens if I multiply the first equation by 4, the second equation by 3, and then I add them? Well, if I do so, there will be 12 here, and they subtract. These are gone. Nice. How many e's do I get? 16 and 9, and both are subtracted. This is minus 25 e's. What do I get on the right? I get minus 75, which is 3 times 25. Let me put it like that, 3 times 25. Somebody really likes me because this is cute, this is luxurious. E is 3. Okay, it's a school problem. Yeah, that's life. Here we go. I'm happy, I'm not criticizing. I'm happy to have it like that. If E is 3, then I put it here, I move it to the other side, and I see that D is negative 4. Is that correct? 12 minus 12 is 0. Yeah, it works. How about here? Negative 16, negative 9, negative... Yeah, it works. So, I have D, I have E, I have all the other guys, and therefore I can write the particular solution. Do I feel like it? No. I'm going to write directly, I'm going to skip directly to the next stage. I just finished stage B. I found particular solution. Let me put it virtually over here, that I get particular solution. And now in the last stage, I'm going to find general solution. And the general solution is done in the usual way. First, I'm going to put the particular solution, and that's where it actually appears. So people will see it if they really want to see that. Here is this crucial part. That's my guess. So for A, I am putting 1/2. Okay, here it comes. 1/2 x squared e to x. Not bad. For B, oh, actually this is my guess also here. So that was for A. For B, I am putting 3 plus 3e to negative 2x plus 13 to make the answer nicer, of course. D is, how much is D? Negative 4. Okay. Minus 4 cosines. And finally, E is 3. So plus 3 sine of 2x. I almost ended it, but this is not the end. This is yp. And little note for those who are curious. This is yp. And now we have to put yh. So, what was lambda? Lambda was 1 actually, of course, because I had a correction. So because lambda is 1, I don't really even have to look there. This is easy. This should be a e to x plus b x e to x, x belonging to real numbers. Okay, I extended the homogeneous brace too far. That's the homogeneous part. Particular part, homogeneous part. 1, 2, 3, 4, that fits. Correction here for the double root. Yeah, that's it. That's it. Okay. So, what should we think of this example? Is it a school problem? The answer is, I mean, exam problem. The answer is not quite, for 2 reasons. First of all, when you come to an exam, you'll get second or third order differential equation with initial conditions also. So after we find the general solution, we should take the derivative and perhaps the next one, depending on the number of conditions, and substitute in the initial time, compare it, and so on. We know the procedure. So in this particular example, there would be 2 initial conditions with y and with y derivative, so we would find the derivative and then work out the initial conditions. That's the first thing. The second thing is that on the exam, I haven't put so many terms on the right. Typically, I put just 2 terms. Why? Because from the 2 terms, I recognize whether you know what you are doing or not. So it's pointless to, to let you work a lot. I mean, you will have enough opportunities to make numerical mistakes anyway. So try to be careful, try to take your time. You will not be rushed at the exam. I always give a lot of time during the exams because I'm not interested in speed writing. I'm interested in thinking, okay? So take your time, do this meticulously, be very careful. Do the intermediate steps, the intermediate calculations, and everything should work out nicely. Okay, don't worry about that. So if you want to see a true exam problem, just ignore 2 parts here or these 2 parts. Or, I put it all here so that we can see everything in one package. We can see the correction for the characteristic number of higher multiplicity. So we recalled, oh yeah, there is this correction. We could see the correction for the right-hand side, which is a different type of correction. We could see this pairing of sine and cosine. We saw everything here, essentially. Okay. So if you know how this works, you can handle almost anything at the exam. So that's it. That's the happy end. What are the limitations of the guessing method? Well, of course, if the right-hand side looks differently, if it doesn't fit into this pattern, then we are out of luck. Another limitation is that the coefficients have to be constant. Otherwise, again, the guessing method does not work. So there is another method which is used. I prefer this one, and I expect you to do that at the exam, but not in the way that if you try something else, I'll be bad, just because I think that this is the easiest way to find a solution. But this other method is also interesting, and some students actually use it. So that's the topic for the next time that we meet. Okay, see you next time. We need to make some room now, and I will try to make this official. I will try to write down the general procedure for this guessing approach, and we will see. And I'm happy with it.